So what has changed? One, we have more parallelism. CPUs have more cores. So I kind of looked up a little bit the data looking from 2010 to 2025. And there's about 16x more cores in a high-end servers than there was at the time, right? We went from 8 cores to 128 cores for a high-end server. AMD is wider. So we used to have 128 bits widths for the SIMD instruction, which basically you can do 4 values at a time. If you have 4 32-bit values, you can do the same operations 4 values at a time. So 4 times faster than doing for 1 value at a time. Now we're 4x that, right? So instead you can do on 16 values at a time. So if you combine those two, that's quite a bit. And I look on the GPU side, they have today about 40x more threads for the GPUs of 2010 to the GPUs of 2025. And GPUs, when you think about threads in GPUs, they work a little bit like SIMD, which is not really doing multiple threads, but each thread is executing the same operation on a lot of data in parallel. It's just they don't necessarily have to be next to each other. And so there's, similar idea. You can do the same operation in parallel many times. And so for the AI, the other thing that changed is for the AI access pattern, right? So we're building those vector stores and need to fetch specific training samples, right? Or you have a secondary index when you can do a similarity search on top of that. And then using this, you have a specialized index for this, and then it points to a certain value in a Parquet files or columnar storage. And so if the smallest unit you can decompress is the page, and you need to decode all the values in that page before the value you need, you have significant amount of work to do to get to a single value, because Parquet, the original encodings are optimized to decode this page very fast to read all the values. So the new use cases, we need more of the random access. That was not a concern at the time. The other argument, which I'm not fully convinced, but it's interesting. I think AI runs in GPUs. So being able to read the data at the speed of AI, which is in the same GPU, right? You have data encoded and we can decode it very fast in that same GPU without getting it from somewhere else, is going to enable AI, because in the future, AI is going to be consuming data more than humans. So that's another argument that we'll see how it pans out. So what can we do about that, right? Like you could say, if you read blog posts online, obviously Parquet was designed at a time when this doesn't matter. Therefore, the design of Parquet is not appropriate for this use case. So actually, I don't think it's completely true, right? There's a healthy pressure created by these newcomers, right? There's a bunch of great research paper for new encodings that are looking at, hey, we need to be able to decode much faster using this modern hardware that is a lot more parallel, right? It is not enough that you can read each column separately and decode each column in parallel. Like within the same column, we need to be able to be much more parallel. So BetterBlocks is a paper on how you stack encodings, ALPs for floating points. FastLanes looks at how to do this fast for integers. FSST does that for strings. So there's a bunch of interesting new encodings coming. And there's been a slew of file formats of people building, wow, okay, we need to build a new file format for the future. So there's a few vector store startups with Lens and Vortex. Lens is speaking at the same time in the other room. And they're doing great stuff, right? And they're putting pressure on Parquet to evolve and get better for those use cases. There's also a few other things like, Meta is working on Nimble, which is more of an API rather than a format, the way they standardize it. There's some research format that came out, FastLanes and F3, and they demonstrate the effectiveness of these new techniques and how that works better for those use cases. So the question is, have things fundamentally changed? And so one argument is actually the layout of those files is not fundamentally different, right? They're still looking at putting chunks of columnar data inside of files and having some metadata to say, hey, look, we have columns and they're stuck encoded together. And then there's a specific encoded for some of those things. So of course, they're trying to optimize how they lay out the metadata to squeeze out every single millisecond out of random access. But however, the format itself is not that fundamentally different. I'm sure people would disagree, but like on the details, mostly the same overall layouts, right? So there's a lot of the same thing that apply on compression of columnar and so on. And I'd like to argue, so it's funny to me, there's a bunch of research papers and they use Parquet as the baseline. Here's these new encodings and it works better than Parquet, right? Parquet is not a fixed thing. You might think of Parquet as a file format, but it's first and foremost, it's an open source project. It's a consensus building machines. And we have a big community that collaborates. So we have a bi-weekly meeting where we talk about, hey, how do we make all the things people want to contribute? How do we get that moving? And in that meeting, you have Databricks, you have Snowflake, you have BigQuery, you have Data Fusion, you have people from CMU, you have people from Dremio, and they're all like discussing how we get to agree so that we make the format better. And my argument is it's easier to popularize those new techniques through the existing machine rather than getting 4 new file formats adopted. And building the community around the project and the fact that we agree on things in this format is the hard part, right? And we stand on the shoulder of giant. Parquet doesn't invent encodings. Parquet looks at the best papers and like listens to what people think is good, and then we adopt it, right? And we do the engineering part of things, which is making sure it's compatible in C++ and it's compatible. And so I'm just an engineer, right? I try to read and understand paper and apply what the scientists are figuring out. So to give an example, over the past year, we added variant to Parquet, which is a new type. You can think of it of a binary representation of JSON. The way this works is basically it encodes it in 2 columns. One column is all the field names, and the other column is all the values. And it maintains a JSON structure, right, in binary in an efficient way. And you can optionally extract some of the values at their own columns, right? So there's lots of flexibility. You have underdefined, maybe you don't have a type. You don't know what the schema of all the columns that exist are. You can put everything into columns, and you can selectively extract some of the values, some of the fields in that structure into their own columns. So they have lots of flexibility for wide things or loosely structured data. So we got to go over this process. This was led from Databricks. Thank you, Databricks, for leading the charge on this. That's usually how it works. One contributor, could be a company, could be an individual, is pushing for something. And the community is going to help this going through, because we need to agree on how we're going to do it. Right. So there was some discussion of where it should be going, whether it was in Spark or Arrow or Iceberg. There was an agreement that Parquet was the most common denominator and all those things. We finalized a consensus on the spec on like agreeing. Parquet is a format. We need a formal spec on how this is going to work. It's not just a library somewhere that we say, oh, it works like this library. And there was the whole discussion on how shredding works and a bunch of details. And then there was a big collaboration, right? In open source, there's the healthy co-petitions. I don't know how many times you have Snowflake and Databricks and BigQuery in the same room collaborating on building something. Like usually there's a bit of the side eye. It's just like, we're doing things better. Nobody's contradicting me, right? And I'm sure there's lots of you in the room. And then we build those cross-compatibility tests, make sure everything's compatible and it's performant and it works and everybody's happy. So we've been talking about those new encodings, right? Like some people have been asking me, well, like, okay, like on one end, we have the OLAP use case. We need to read a lot of data. On the other hand, you have the random access. You need to read one row in the whole thing. Aren't those use cases at odds? Well, it turns out you could think, yeah, you're right. But actually, when you think of how this actually works, the main thing, right, if you think about those new encodings, those new formats, and how you make random access possible, both better parallelism to get more throughput and random access to read one value, the fastest as possible, they both rely on the same thing. They rely on having encodings that avoid data dependencies, right? And because whether you want to read all the values in parallel very fast, or you want to read the nth value very fast without having to read the other values, you have the same characteristic to the encoding. They both rely on not having to read all the previous values before reading that value, right? If you want parallelism or you want random access, it's more or less the same similar characteristic enable that. So when you have data that doesn't vary very much, like, I don't know, you have timestamps or you're measuring a metric or something, delta encoding works well, right? You capture the difference from the previous value because it doesn't vary very much, and you have smaller integers and you can compress them better. So of course, the flow of this is you have to read all the previous value because you decode the nth value, right? And you have to decode them in order, so you cannot much parallelize if you do a naive implementation of that. And it's a bit the same for the block compression or general purpose compression, like the LZ for LZ family algorithms or Z standard and all of that. They have a tendency to modify their states as they compress or decompress because they're more optimized to compress or decompress a stream of data. And so in the same thing, you actually need to decompress you cannot decompress from the middle if you use just this kind of compression. So you need those new encodings. And so if you go a little bit in the more details, ALP is for encoding floating points. And basically it turns floating points in good integers that are going to be easy to compress, easy to encode as integers. And it's based on the fact that most of the floating point values are actually decimal. And so it can compress them much better. FastLanes is a few algorithms that decides how to encode integers in a very fast way, whether you do run length encoding on bit packing and to take advantage of SIMD and very parallel processors. FSST encode strings, and by encoding subset of the string with a dictionary, instead of taking the entire string, right, you split it into repeated substrings, right? And so, for example, the first line becomes 063, 0 is http://, 6 is in.tum, and 3 is .de, right? So you encode a string into more compressed string by creating a smart dictionary. A lot of the papers about how you build that dictionary in a very parallel way, taking advantage of SIMD and all of that. The advantage of FSST is you can, if you do an exact match filter, you can do it on the encoded data, right? If you take the value you're filtering by, you encode it using the symbol table, and you can just do exact match on everything and it's going to work, right? So you can evaluate certain things on the encoding data. That makes it very fast. I'm going to accelerate a little bit because I'm going over time. 5 minutes. That's good. And BetterBlocks is talking about, this is all about, you can stack some of those algorithms, right? So they talk about lightweight encodings. Lightweight encodings are these encodings that are going to be very parallelizable, and they specialize for a specific type, and they're trying to do no branching, no data dependency, so they can go as fast as possible on this modern hardware that does things very much in parallel. So BetterBlocks is trying to stack those algorithms. So maybe you do this smart delta on top of bit packing or other things, and their strategies to pick the best combinations. So concrete next steps. So first, I'll start with the boring things. There are things you can do today in Parquet to make random access better. And it has row groups, but you can have only one. Parquet pages force you to decompress too many values, but you can make the pages smaller. You can control how big the pages are, and they don't all have to be the same size, right? So if you have some columns where you need one size, other another size, the pages can be any size and can be completely heterogeneous. You have lots of room to decide that. General purpose compression is too slow, or it forces you to decode the whole thing. Well, it's optional, and some encodings don't allow random access. Well, you can also pick what encodings you want to use on when you write the files. And so those are the boring things you can do today with Parquet, right? Maybe be a bit more selective when you pick how you write the file. Another question is, we talk about metadata and how it can get too big. So now with the addition of variants, I could argue that when you have columnar data, you kind of try to fit a whole bunch of data into 1 gig. If all the columns are very dense and you have 1 million columns, you're going to put very few rows in that, right? So it's not going to get degraded performance with columnar representation. It's not just like Parquet, right? It's columnar representation in general. If a subset of columns are dense and the others are very sparse, what happens often when you have 1 million columns, what happens is you have a few dozens of columns that are normal, right? Like it's very dense. And there's a long tail of columns that are a few values each. So that's where variant can be a great thing, because instead of, creating a bunch of tiny columns next to each other, you can just combine all the very sparse column into 1 column or 2 columns in this case, and be a little smarter about how you store them. And because you're not going to access it in the same way anyway, right? We can also do a better use of metadata. I think in the new things, length, for example, is at the same time a table format and a file format, right? So there's a bit of discussing, do I care how the metadata is stored in the file versus in the table versus in the database, right? Like you don't necessarily need to access the metadata as it's stored in the Parquet footer, right? It's just a source of truth for it. You can externalize it somewhere else. You can put it in an index. You can put it in other places where you're going to be able to access it a lot faster. And maybe it's not that important that the source of truth of it is not as efficient as other things. So we are actually adding those new encodings as we speak. right? Parquet is based on research, and we keep integrating new ideas. So to enable random access and more higher throughput decompression, we need those new encodings and this improved metadata layout. So ALP, there's a proposal in progress. You can follow on the Parquet mailing list. Their archive is online if you want to look. FSST, there's also another proposal in progress, and another one on the improved metadata, which is about rewriting the footer in flat buffer. And they're all led by different contributors, one by Snowflake, one by Databricks, one by Uber, if you're curious. But everybody's giving feedback and contributing to how do we get to a consensus on these things. Right. And you can extend Parquet, right? You don't have, it's not either you create your own format or you contribute to Parquet, right? I think the only thing that we need to agree on is the encodings. Of course, it's the way the data is encoded. It needs to be in the bottom layer of the storage. That's kind of the core of the format. But at other things like having secondary indices or things on that nature, whatever that means to your use cases, you can build that on top, right? So as soon as we make random access work better by adopting those new encodings that enable random access, which is I can read the nth value directly without reading anything before and buying as little as I can before I read that value. We enable a whole bunch of use cases where people can have those indices to be vector stores and things like that. And there's a nice blog post in the Data Fusion blog about embedding custom indices in Parquet, which is something you can do already. Like Parquet enables random things in between columns, right? Because you have the footer. That's my last slide. The footer that points to where each column is, then nothing that prevents you to put random things in between the columns or in between the row groups or in the page headers because it's encoded in Swift and you can add your own custom IDs in there that are going to be ignored by other readers. So you can embed things in a Parquet file, make it custom so that it's still compatible with the rest of the ecosystem for read, but it contains extra indices that are going to be useful to your right? So it's not either or. You don't have to build a whole new things. We can make Parquet better for the random access, and then we can build a bunch of things on top of it that don't have necessarily to be in the project. And you can move faster and do things.